Well, welcome to part two of the virtual lecture. I'm sure you're entertained by now, but we will continue and look at the phase diagram. And so basically all I'm going to do here is show you what you need to know, and then it's how to navigate around one of these things, what's going on, what's happening where, all that kind of stuff. So on this right now, we've got several points. Let me label these. We'll call this one A. We'll call the one at the top over here B. Down at the origin or near there, we'll call that one C. And then B. Okay, so we're going to look at these things individually. So I guess the first thing we can do is figure out what goes where in terms of phases. So any one of these things that you see is going to be split into three different parts. Your graph area will be split to three different parts. This one here, this one here, and this one down here. And no matter how you slice it, no pun intended, this region is the solid. This region is the liquid, and down here, that whole region is vapor. So what then happens is we have different segments, different lines again, sort of like what we saw in the heating curve. We have a segment C to A, a segment A to B, and a segment A to D. So we're going to look at what all those are. First thing to note, though, is what is point A? A is the triple point. And at the triple point, this is going to sound maybe a little bit strange if you're not familiar with it. The solid, the liquid, and the vapor are present. All of them at the same time. And so this looks kind of strange. You can find videos where people investigate substances at this point. But that's an important thing to know. It's called the triple point because all three phases exist simultaneously at the same time. And note that it's the intersection of all three segments that I mentioned earlier. Okay? So that's the triple point. What then would we call this segment here? C to A. That is what's called the sublimation line. Because if you look what happens, if we took a point that I'll put here and call that point Y, call it whatever you want, what would happen if I at constant pressure heated material? That's not a straight line. Heated the material such that we crossed that line. Visually, what would happen is you'd have a solid and it would turn into a gas. It would look like it disappears. Now, there is a substance that does this that you may be familiar with. It's called dry ice. What dry ice is solid carbon dioxide. And at ambient pressure, meaning the pressure in this room or the pressure in the lab or the pressure outside, what have you, the solid would appear to disappear. It would appear to vanish. Because what it's doing is it's turning into a vapor, skipping the liquid phase. But that only happens under certain temperature and pressure conditions. So C to A is the sublimation line. The other thing to note is what phases are present along these lines. And so over here, where point Y is, where we start, it's only solid. When we get to this place here, where we transitioned to the vapor phase, only the vapor is present, but along the line, solid and vapor are present. So that's an important thing to note too. Okay, we equally could do the following, just FYI. If we kept the temperature constant, and drop the pressure such that we cross that line, the same thing would happen. You also could go diagonally, right? You could change the temperature and the pressure at the same time, and that would occur. All right. What would happen if, at point X, I kept the pressure, keep my pressure constant, and I heat that such that that crosses that line, segment AB? Your solid would appear to melt. Consequently, segment A to B is the fusion line. And so we could also call it the melting line. If you start in a solid and you cross that, it turns to a liquid. And the reverse, if we start over here at point Z, go the other way, we keep the pressure constant, lower the temperature, it freezes. So along that line, solid and liquid are present. Okay? So if I'm anywhere along that line, there's two phases. If I'm to the left of it, it's solid. If I'm to the right, it's a liquid. So that's the fusion line. And the final segment then is A to D. Along that line, at any point, there's both liquid and vapor present. Anywhere just off the line in this direction, it's only liquid. Anywhere off the line in that direction, it's only vapor. And so from point Z, if, again, I kept the pressure, or sorry, the temperature constant, lower the pressure, when I cross that line, the liquid turns to vapor. And so this also is something you may have seen, because if you're using one of these RotoVap devices that I've referred to before, what you do is you have your solvent in a flask, and you stick it on this device, and you lower the pressure. You don't even have to change the temperature. If you just lower the pressure, it evaporates easier. And so that's what occurs there. And so those are the major components of the phase diagram. All right, so what you'll need to be able to do is identify what phases are present along any one of these segments. Here along that line, solid and vapor. Along this one, solid and liquid. And along the curvy one here, liquid and vapor. Identify the triple point. That's a good thing to be able to do. And also, what would happen, let's say if I start somewhere over here and I transition to here, what would happen with the sample? So those are the things that we need to know for phase diagrams. This is on the exam. It's also worth 15 points. So keep that in mind. Finally, one thing that's important to summarize here is the energetics of these phase changes. Now, we've done this in class, but let's just sum it up into one chart here. These phase changes can be endothermic or exothermic. Endothermic means you have to put energy in for the phase change to happen. Exothermic means you have to take energy out to make the phase change happen. And so the first one, that's endothermic, is melting or fusion. Its reverse is exothermic. So in order to melt something, you have to put heat in, or energy in some form. In order to freeze something, you have to take energy out. So how we do this with water, you take the ice cube out of the freezer, you're changing the temperature from 0°C to whatever the temperature of the room is, it'll melt. To freeze water, what do? You put your ice cube tray with liquid water in the freezer. It goes down to -15, whatever it is. It freezes. You're taking energy out. So this is a little weird in the sense that it says it's exothermic, and so you might think, well, if I touched it while this process was happening, I'd feel heat. You don't. But what you're doing is taking energy out. So remember, these terms are all from the perspective of the system. So when water freezes, the system, the water, sees energy leaving. When ice melts, the system, the ice, sees energy coming in. Okay? Boiling is endothermic. You have to heat a liquid to evaporate it. Condensation is exothermic. You have to take heat away from a vapor to condense it back to a liquid. Same thing, for the same reasons. And finally, the last one is sublimation and deposition. They're opposites of one another too. Again, sublimation is when we go from the solid to the vapor, skipping the liquid phase entirely. So for dry ice, if you go to a food pyramid or wherever to buy it, it's in a really well insulated cooler, a freezer actually, not a cooler. You take it out, you put it on the table, it would appear to vanish, meaning it's turning into a gas. You change the temperature from whatever it's at, -78°C, to, let's say, room temperature, 25°C. You're adding energy. It's endothermic. The system sees energy coming in. On the other hand, if you had a balloon full of carbon dioxide gas and you put it in something pretty cold, liquid nitrogen does the trick, which is at 77 Kelvin, you would find a solid form inside your balloon. Deposition. You have to take energy out. So it's important to remember the sign, if you will. Positive delta H, negative delta H for these things. So that's basically all you need to know about these two subjects. There will be material like this covered in lecture. Dr. Mader will give his own spin on this. So between the two of us, I hope you can figure this out and understand how to answer the test questions for it, and also the homework questions that will involve it. Again, you can read about this in the book too. So if you have any questions about either one of these topics, please don't hesitate to email me. I will have email in Japan pretty much constantly, but again, it is 14 hours ahead, so I might not respond right away. So thanks for watching, and good luck.